Proto-Danksharding, the Ethereum data blob system, has unlocked about 200 TPS for ETH L2s. In the next couple of years, we'll have full DankSharding, which should give us a theoretical maximum of 50,000 TPS. EigenDA, which is EigenLayer's DA system, already today has about 10x the capacity that full DankSharding will eventually give us, which implies about 500,000 TPS available now in a sense. And longer term, the goal is 750x, which implies almost 50 million TPS. In this video, I'll explain how all of these things work and what the implications are of that kind of scale. Note, this video was made in collaboration with EigenLayer, but my goal here is to explain how these things work, not endorse them, so do your own research, not financial advice. The way that I'm going to structure this video is I'm going to start by explaining Proto-Danksharding, the existing data blob system, and this is a really good intro because it's actually very simple. Then we'll get into full DankSharding, which is a little more complex, and we'll talk about erasure coding, data availability sampling, sharding, etc. And then finally, we'll have all the context we need to understand EigenDA. And I'll explain how that works and how it's similar but different and how those differences allow for greater scale. And we'll talk about the implications of that level of scale. But before I get into all of that, I want to first put all of this in context and just talk for a second about what DA is and why it's important. So in Ethereum's rollup-centric scaling vision, we have a bunch of these L2s running on top of Ethereum, so to speak, inheriting its security. But in order for these L2s to function properly, they need to do two main things. First, they need to, in the case of ZK rollups, have their ZK proofs verified on-chain on Ethereum. For optimistic rollups, they need to have their fraud-proof adjudication stuff running on Ethereum. And then two, these systems need to post some data to a data availability service. And the exact data that these systems need to post depends a bit on what kind of system it is. For an optimistic rollup, which is what I'm depicting here, they need to post all of their transaction data to the DA service. So here I'm showing the blockchain with some transactions, and these transactions are taken and compressed a little bit because we can compress them, we can strip out some information. Those compressed transactions are bundled up and sent to the DA service. And so with optimistic rollups, as I said, we can compress and take some of the information out of those transactions, but we need a record of every individual transaction, every action, every step which the system took to arrive at some state. Now, for ZK rollups, it's a little bit different. You don't actually need to make available every little action, every transaction, because we actually have a ZK proof which gives us confidence, which proves to us that the new state of the system is in fact the result of a bunch of valid transactions. It's the correct execution of a bunch of transactions, and the ZK proof proves that, so we don't actually need to see those transactions. What we do need to see, though, is the net result. Like, okay, what is the new state of the system? So here I'm depicting that. I'm showing the blockchain and a snapshot of the world state as it was at some point in history. Then a bunch of blocks happen with transactions. We get some new world state. And the thing which we post to the DA service is the difference between this new state and the old state. So how have the contracts changed? How have the accounts changed, etc.? We bundle that up and send it to the DA service. I'm also showing the ZK proof generation, just as a side note, where we take the old state root, the new state root, and the transactions, and we use all of that data to generate a proof of this transition to this new state. And that proof goes to Ethereum. So one point I'll make about DA systems in general before I get into Proto-Danksharding, and you probably already know this, is just that these systems are not like Dropboxes, they're not long-term storage. They're more like a highly available bulletin board kind of thing, almost like a data distribution channel or hub, where we just make data available there for like 2 weeks or so. And that's why I've drawn these systems in this way, so I'll explain this briefly. This is meant to be Ethereum, the Ethereum world state, with a bunch of contracts as these little cubes, and these narrow rectangular sections are meant to be accounts. Then I've got the ETH DA system as this ring going around that, and the reason I've drawn it as a ring is because as data is written to this DA service, in a sense, the most recent, the newest data being added is overwriting the oldest data because there's an expiry on this data. So in a sense, it has like a fixed ongoing capacity, and then the new data is just overwriting the old data almost like a ring. It's like a clock going around in a circle. And it's the same thing for the EigenDA DA system, which I've drawn here. But this system I've just drawn as bigger because it has a lot more capacity. And finally, both of these systems are, of course, backed in slightly different ways by the Ethereum staked capital. So now I will get into Proto-Danksharding. Ethereum data blobs are attached to the Ethereum blockchain, sort of in the way that I've shown here, where on the Ethereum blockchain, there will be a transaction, a blob carrying transaction, which points to one or more blobs. And that transaction will contain a fingerprint of that data. And that transaction will, of course, live forever in the Ethereum blockchain. That never goes away. But the data itself, which the transaction points to, can eventually be dropped, at least by most of the nodes. And the way that this resource, these blobs are sold, of course, is that we have a target and a maximum number of blobs per block. Right now the target is 3 and the maximum is 6. And this is a lot like EIP 1559, where we have a target utilization of some resource and a maximum which is higher. And that allows for certain flexibility and more efficiency in certain ways, which I explained in that video if you want to watch that. Briefly, the way that this EIP 1559 fee kind of mechanism works is that if you're below saturation, if you're below your target, the fee will continually drop. So if you're even a little bit below the target, the fee continually drops until it hits a floor. In this case, the floor was 1 way, which is very low. Then when we hit saturation, the fee kind of goes into price discovery. Anytime you're above the target, the fee will increase exponentially. So when you hit saturation, rapidly you enter price discovery and you get a non-zero fee. Now, one other interesting thing that I'll mention here is that this DA service is like the first additional service that Ethereum has offered since inception. So the main service that Ethereum sells to the public is compute time, so to speak, on the world computer. Execution, storage for contracts, like resource use in this world computer, that's the thing which it sells primarily. That's what the block space is selling, really, the gas. And this DA stuff is a separate, distinct service. It's this bulletin board thing, which is distinct from the world computer. So because these things are distinct, you have 2 fee markets now, right? You have the regular fee market and then you have the blob one. And so each blob is worth or costs a certain amount of gas, 131,072 exactly. That's how much gas each blob costs. And that's just 1 gas per byte, by the way. But this gas is being sold at a different rate to what the regular Ethereum execution block gas is sold at. So we have a separate market, right? And this, the price, the ETH per gas that you need to pay to use this blob storage, that is determined algorithmically, as I mentioned in this EIP 1559 kind of way. And all of that fee is burned. Now, an important question we can ask is how much data blob throughput are we offering? And what is the storage burden that places on the Ethereum nodes? And so the amount of storage required is determined by the amount of blob history that we need to store. So ETH blobs are stored for 4,096 epochs, where each epoch contains 32 slots, 32 potential blocks. And that works out to 18.2 days. So all of these nodes, every Ethereum node, is expected to store the most recent 4,096 epochs worth of blob data. And so the throughput, given that we have this duration, we get 51 gigabytes of total capacity, and the throughput that we can offer to the world is 32 kilobytes per second. So you can read through the math here, but that's basically how it works. We have no sharding of this. Every node stores all of this data. And this capacity allows for a certain amount of scaling. One more point I'll make actually is that this storage may not seem like a lot. 51 gigabytes is not a lot of storage. It would seem we could crank up the blob count, but it's actually more about bandwidth than storage. We can't just sort of carelessly increase the blob count. We have to consider the bandwidth and the storage. So this throughput gives us a certain amount of scaling. So what I've got here is L2 on-chain costs, which are the expenses that the L2s are paying to Ethereum in order to run their systems. Then we have the average transaction fees, which is what the users are paying to use those L2s. And of course, these two things are related. Higher costs will translate to higher fees for the users. And we can see where 4844 was introduced because there's a huge reduction in both of these. So previously, these L2s were using the Ethereum blockchain as their data availability service. They were posting that data that I mentioned at the start of the video. They were throwing that data right into the blockchain and using that as their sort of bulletin board DA service. And the problem with doing that is that there's a limited amount of space there, and you're also competing with the other users of Ethereum who are trying to do DeFi transactions and whatever else. You're competing with them for that block space. So with 4844, we expand this overall DA capacity, and we introduce something which is purpose-built for DA, where you're not competing with those other users, so it's much cheaper. So yeah, as I mentioned, this is pulled from one of Vitalik's blog posts where he calculates, given the current DA capacity, we have about 173 TPS available for these L2s. And that is pretty much what we're hitting right now, actually. And so one other thing I'll mention is that ZK rollups can be more efficient in a certain way because they don't have to post all of the transaction data, like information for every individual transaction. Because they don't have to do that, and they can do the state diff thing I talked about at the start, they can, in certain circumstances, exceed this scaling. Like they can cram a lot of transactions into a small amount of data that they need to post to a DA system. So there's some nuance there. ZK rollups can potentially scale higher, but this is the basic amount of scaling that we get given the current 3 blob situation for Ethereum blobs. But of course, the plan is to increase this a great deal, which brings us to full DankSharding. Okay, so we're going to increase our blob capacity from a target of 3 with a maximum of 6 to eventually a target of 128 with a maximum of 256 blobs per slot, which is a 43x increase. But in order to do that, we can't actually just require all of the nodes to download all of that data because it uses far too much bandwidth and a lot of storage, and it's just way too much. So we need some way of sharding that data, these 128 blobs. We need to somehow shard that data across the set of nodes such that each node is only having to download and deal with a small fraction of that data. And the problem, though, with simply sharding that data and calling it a day is that we need the Ethereum network to be certain that all of the data is available. So if you're a node and you're only downloading 1 out of every 32, say, blobs, you need to be sure that those other blobs are available, right? Otherwise, the network is not functioning properly. It's not like, or you don't know that it's actually functioning properly. You don't know that it's doing its job and that all these systems that run on top of it are secure, etc. So you need some way to know that if for some new block that comes in, if some of that data that is supposed to be paired with that block is not actually available, you need to reject that block, right? So the consensus part of Ethereum needs to be doing the filtering. And if data is not actually available when it should be, it needs to reject the block, right? So, but the question is, how do you do this if you are only downloading 1/32 of all of that data? So the sort of naive way to do it would be, okay, I'm going to request to these other nodes I have the 1/32 of it, so that portion of the data I'm confident about, right? But I'm going to request to these other nodes for those other chunks. But obviously I don't want to download all of the chunks. I just want to maybe randomly sample and say, okay, you have this blob that I don't have. I don't want to download it all, but I'm going to ask you for 10 random chunks out of, like, say there's 4,000 chunks in a blob. I'm going to ask for just 10 of those. And if you respond with those chunks correctly, I'll assume you have the rest of the data because I randomly selected them. It's like a decent chance that you have all the data. But the problem with that is that if there might be one chunk in there which is very consequential, which correlates to some transaction worth millions of dollars. So if I'm just randomly asking for 10 samples out of 4,000 and you're withholding just one of those, the odds that I hit that one is low, right? So that's a problem. So we need some way to sample, some way that I can ask for a small number of these chunks and be certain that you have the whole set of data. And to do that, we need data availability sampling, which I'm going to explain. But in order for data availability sampling to work, we need first erasure coding, which is what all of this is about, and I'll explain that now. Okay, so each blob is 131,072 bytes of data, and this data could be anything. It could be transactions for our optimistic rollup, or it could be a JPEG. Ethereum really doesn't care what kind of data you put into a blob. It just views it as data, as zeros and ones. And this chunk of data, or this blob of data, we can interpret it as 4,096 32-byte chunks. So we can split it up into chunks. And then each of those chunks, each of those 32-byte chunks, we can view as a field element or as a number. You can think of it as a number. And so here's my representation of that. You've got your data blob with a whole bunch of chunks. In reality, there's 4,096. Here I've drawn a fraction of that, but you got a bunch of these little chunks. And if you zoom in on one of these chunks, you just see data, right? Like this could be a JPEG or it could be a bunch of transactions. And when you zoom in on an individual chunk, in reality, this is a chunk of a JPEG or it's 2.5 transactions or whatever. But you can just see it as a number, right? It's just zeros and ones, right? It's 32 bytes of data. And so what that allows us to do is that allows us to interpret this whole blob as a polynomial. We can sort of transform this, what used to be a JPEG, what used to be a bunch of transactions, into first a whole bunch of these numbers, and then that can be transformed or imagined as a polynomial. And I'll explain why we do that in a second, but first I'll just briefly say something about the finite field thing. So these numbers are not just kind of normal real numbers, they're integers, and they're integers over a finite field. That's how we're interpreting them, right? And I've done a video where I talked about finite fields, but all I'll say is that rather than having like a number line that extends to infinity, with a finite field you have something like a loop or like a clock, where once you hit the maximum number, if you keep going, you roll over to 0. So it's contained in a certain way. And you allow for your mathematical operations to work within that, and it has certain properties, et cetera, et cetera. But it's basically a number. So once we have all of these points, as I was saying, you can transform this into a polynomial in the following way. So first imagine that you have some predetermined set of x values, like x equals 0, x equals 1, x equals 2, etc. Well, then we can look at our chunks here from our blob and say, okay, this first one is going to be the y value corresponding to the first x value. So for x equals 0, we're just going to imagine that that evaluates to a y value of whatever this number is. For x equals 1, here's the y value. For x equals 2, here's the y value. So then what we have is we have a whole bunch of x values and a whole bunch of corresponding y values. And given all of those points, we can fit a polynomial to those points. And so then we have our polynomial. Now, why do we want to have a polynomial? Well, what we can do with a polynomial like this is we can grab a whole bunch more points within that polynomial. So if these are points in a polynomial, we can extend these points to include a whole bunch more points that we choose from within this polynomial. I mean, that's what I'm drawing here. Here's the initial data and the polynomial that corresponds to. Then we can extend the data and grab a whole bunch more points, 4,096 more points. And it's the same polynomial, it's just more points, right? And so then we've doubled the size of our data. And the intuition for why we do this is if you think about a line on a graph, you only need 2 points on that line to reconstruct the equation of the line, right? So if we have 4 points initially, any 2 of those points are sufficient for you to reconstruct the line, and therefore the initial points, right? The initial data. So it's the same thing here. There's just more, it's a higher degree kind of polynomial. So when we extend the data like that, what that means is that any 50%, any 4,096 of those points, of those 8,192, are sufficient to reconstruct the polynomial and therefore the initial data. So that allows us to do our sampling in a much more robust way. Because now if you're trying to hide that little single chunk of data, you need to prevent me from constructing the polynomial, right? Because if I can construct the entire polynomial, I know what that piece of data is. So you need to withhold actually not just one chunk, but half the chunks. Half of the chunks plus 1. If I can get any 4,096, I can reconstruct it all, and you're no longer able to withhold that data. So this makes the sampling much easier for me because I just ask for, say, 20 random samples, and the odds that I don't hit some of that 50% of this set of numbers that you're withholding is crazy low, like 1 in a million chance after just 20 samples, because, you know, it's like throwing random darts at this line, and as the data withholder, you're hoping I never hit the entire right side, let's say, even though I'm like blindly throwing the dart. So the odds are a lot better in that sense. And finally, the way in which I know that one of these chunks, like I'm asking you for these chunks for a blob, which I perhaps do not have, right? So how do I know that the chunk you've returned is correct? You could just give me random data. And the way we actually know that is through KZG commitments. So each blob will have a KZG commitment, which is written onto Ethereum. And that KZG commitment is like a Merkle root, where with a Merkle root, you can take some single chunk of data and check that it belongs to the root, right? Assuming you have a little extra data, but you can check that it belongs, right? And it's the same thing here, but this is for like a polynomial. So given one chunk of data or given 1 point or a few points, I can verify that that actually corresponds to this polynomial that was committed to without having a bunch more data. So that is erasure coding, which allows us to extend our data in that way, which allows us to sample and be certain that data is available without downloading it all. And this is how we allow for the data to be sharded. So the way that this data is sharded is that we have 32 subnets where basically each Ethereum node is going to download just 1/32 of the overall blob data. And every node, of course, will sample for the whole range of data, but they will only themselves store 1/32. And this works in kind of the way that I'm trying to draw here, where it's not as if each node will download 1 out of every 32 blobs in its entirety. Instead, a node will download 1/32 of every blob. So like this node here is downloading this last fraction of all of the blobs. So in that sense, the blobs are sort of striped across all of the subnets in the network. Now, I'll just say like a few words about two-dimensional data availability sampling. It's, you know, probably more of a rabbit hole than we need to go on now, but basically if you have a situation like this where you have all of these different blobs, like a lot of blobs, and let's say you want to do 20 samples on each blob to be sure it's available, right? You want to sample across these blobs. Well, if there's a lot of blobs, you have to do 20 samples for every blob, right? Which can end up being a lot of samples, right? What you could do is you could, in addition to horizontally erasure coding the blobs, the data, you could also vertically erasure code, which could allow you to like sort of stretch the set of blobs in, like, imagine the set of blobs is like one chunk of data. You could stretch it, erasure code it vertically, and then you could sample across that whole two-dimensional thing, and you could do like 50 samples, and you'd be covering the whole, all of the data. And I maybe won't go into more detail because it's kind of weird to think about, but that is a possibility in the future. One of the reasons I'm not going into that a lot is because we might just stick with one-dimensional DAS. This is from Vitalik's blog post. So we might not even do two-dimensional, so we'll see. But in any case, the result of all of this is that we get scaling, right? 3 blobs right now is like 200 TPS. Full DankSharding will hit 7,500. That's without compression of the data which is being stored in the DA system from the L2s. With compression, we get to like 58,000 TPS. And here's Vitalik's writing on that. That's where I got these figures from. And finally, I'll talk about EigenDA, which achieves vastly, vastly higher degrees of data availability, throughput, and therefore scale. So EigenDA has some key architectural differences, which allows it to scale horizontally, which is something that Ethereum does not do. So what I mean by scale horizontally is that as we add more computers to the EigenDA operator set, we can offer more DA capacity. It can just expand with the number of machines, right? And in Ethereum, this is not how things work. Even in full DankSharding, when we have our 32 subnets, we don't actually get more scale as we add more machines. Like if you're a new Ethereum node being added to the network, you essentially are just shuffled into one of the 32 subnets, and you're just storing data that those guys were already storing, right? So you joining the network are bringing more redundancy and more robustness to the network, but no more scale. The throughput of the system is exactly the same, right? And this obviously limits the throughput. Like if we want more throughput, eventually we have to start scaling horizontally. And so the way that EigenDA does this is, first of all, blobs are erasure coded at a higher ratio, at a different ratio, 4.54. So rather than doubling the size of the initial data, it's multiplied by 4.54. And this data is then dispersed to the operators through a disperser. So the disperser is going to basically break this up into chunks and give the chunks to operators in proportion to how much restaked ETH is backing them. But when you're doing this, you are not duplicating the storage. So you're not, for example, like this little chunk of data here that is being stored by this operator, this chunk of data is not being stored by anyone else, right? So this initial data the initial data was erasure coded and expanded. Then it's just being distributed across these nodes. And so there is redundancy in the sense that the erasure coding means that we only need 1 over 4.54 of the data to recover the initial data. Like we only need that fraction, right? That's just a fact of erasure coding. And then we're just distributing all of that across these nodes. So we still have some redundancy, but we're not adding additional redundancy on top of the erasure coding, right? Whereas in Ethereum, you essentially you have like 2 layers of redundancy. You have the erasure coding redundancy, and then you have a subnet with like 100 nodes in it. So each computer is redundantly storing the chunk that it's storing, right? So anyway, that allows us to achieve much higher scale because as we add more computers, we can distribute more data, we can feed more data into that network, we can distribute it across those computers. And another point is that we have no P2P, so the communication, the way this data is distributed is not in a P2P manner. P2P is very inefficient because there's a lot of overhead, there's a lot of repetition in terms of the messages that are passed around. If you have a disperser, you can avoid that P2P and reduce the bandwidth requirements a lot. Basically, the disperser is like a high-end server, will disperse that data to these underlying operators, and that's much more efficient. So, and a brief point on how this works. So the disperser is going to take the DA blob, distribute it to these operators, and these operators are going to respond with a signed message, a commitment to this task, right? They're committing to the job of storing this data for the 15-day duration or whatever. And because we're going to have a signed message, a signed commitment from all of these operators, and that message is going to be written onto Ethereum, that allows for potential slashing, right? So now they've really committed to this work. It's on Ethereum. That record is there. And if they fail in their duties, they can potentially be slashed, right? So anyway, the main point is that this architecture, with especially the no replication thing, allows for this large degree of scaling because we can horizontally scale the system. And another point is that these nodes, these operators, like remember all of these, this is the entire set of the Ethereum validators. And these machines here are eigenlayer restakers who've also opted in to be EigenDA operators. And so they're simultaneously doing their Ethereum validation work and then also running this EigenDA service. But these machines, because they're opting into all of this, they can run higher end hardware. They can have high-end SSDs and have high bandwidth connections. And so they can handle way higher DA capacity and throughput than we can ever expect the regular old Ethereum validator set to handle, because we want these machines to be able to be low-end, consumer grade, whatever, right? So having this system, which is sort of grown out of the Ethereum validator set and which is opt-in, we can therefore take that set of computers, make them much higher end, much faster, without any downside to the Ethereum network. And so not only can we scale horizontally as we add more machines to that, we can also crank up their parameters so that each of them is handling more capacity. And all of that, of course, is backed by the Ethereum restaked capital. So now here's a representation of what that kind of looks like in, I don't know, multiple dimensions, where same idea as above. We have our operator set, we have the ETH, which is backing them, and then the data for these data blobs that come in over time is distributed in proportion, sort of pro rata across their restaked ETH. And then this data is stored for 15 days. So we have this like moving set, this moving like structure of data where you could imagine new data is added here at the front, and then the old data, which is expiring, is kind of dropped off the end, like a sort of assembly line or something like that. Now, the real important end result of all of this, like the reason we have this different architecture and horizontal scaling, et cetera, is to achieve higher scaling, right? So here's just a little review of the different scaling figures for these different systems. Proto-Danksharding gives us about 200 TPS, about 1400 with compression. Full Danksharding, as I said, we can hit about 50,000 TPS if we have the L2 data compression as well. Then with EigenDA, we have already capacity for 500,000, 600,000 TPS with compression. And then longer term, the goal for EigenDA is to hit eventually 1 gigabyte per second, which, as I said in the intro, would imply 40 to 50 million TPS, 43 million TPS. And, you know, that's a tremendous amount of scale, obviously. And this level of scale is the kind of thing that you need to run certain systems. So Mega ETH, for example, is forthcoming and plans to have 100,000 TPS right away at launch and very low latency, which is important. But they're only able to do that because they're going to use EigenDA for their data availability service. Like ETH-DA does not have capacity for that, right? And won't really, like maybe ever, for that level of throughput, right? So with part of what EigenDA is doing and what EigenLayer in general is doing is taking and accelerating, in some sense, the Ethereum timeline, the Ethereum development. Like whatever the capacity is of Ethereum now, EigenLayer is in a sense allowing for like an expansion of that ahead of, faster than Ethereum can achieve those things. And some of those things that Ethereum won't ever achieve, right? Like I don't know if the ETH-DA will ever hit 1 gigabyte per second. I mean, I don't think so. I think that's unrealistic. But this level of scale, I think when we hit this level of scale, or when we hit, you know, 1,000 TPS, 10,000, 100,000, a million, 10 million, like at each order of magnitude, I think you probably need to do a pretty blank sheet of paper reimagining of like what you can do with that system. So the obvious stuff is like global financial payments and ultimately the entire global financial system and economic system. If you can hit, you know, millions of TPS, it seems to me you could run essentially the entire global financial economic system. All that activity can happen in this thing, in like this extended world computer. And so that is obviously huge, right? Truly. But as you get into those levels, like I think there's more as well that you can do. Like there's the, you know, included, I guess, in the entire financial activity would be the 24/7 like markets for various assets, derivatives, huge amounts of like high frequency things like that. That can all increasingly happen in a extended world computer. But then also things like microtransactions for digital services, right? APIs that you know, various systems use to grab data and information and all these different things. Those can be paid for with microtransactions if we have this level of scale. AI, we can have microtransactions for the use of various AI models and a million other things, right? So this digital economy just expands and includes more fine-grained, detailed actions. More of those things can be consumed by this world computer, which is growing like a black hole or something, right? And here's a point that is very interesting, which I hadn't thought of, which I spoke with some people from EigenLayer and they brought this to my attention, is you could even maybe have with this level of scale where the cost per transaction is so low, you could have things like airline booking, ride sharing systems, maybe like house sharing, you know, like the Uber, Airbnb, airlines. Like this stuff is like this kind of public infrastructure, public/private sort of infrastructure kind of stuff. And these systems, like the way they work is you have some backend server run by the company that runs them or the airline or whatever. And that backend server is handling the logic for that system, right? They're doing the matching of the rides, allowing you to book the flight, all of these things, right? And that's being done by this backend server currently. But if you have a system that has this level of scale, you could potentially just run that kind of backend logic, infrastructure kind of logic, as a roll-up, right? You could just have each of these actions you might take in a system like that, they could be transactions. You book a flight, that's a transaction. You even call for a ride, that's a tiny little transaction that costs virtually nothing. So then when you have something like that, you can have this new sort of paradigm of public infrastructure, these systems which allow us to travel and all this stuff, like public infrastructure can then run as a transparent, auditable, like system as a roll-up that, you know, it becomes like a public good, right? So with this level of scaling, you can potentially do that. You can this, essentially what happens is the world computer kind of thing starts to consume more of the computational structure that runs our civilization. And as far as I'm concerned, the more of that structure that the world computer can consume, the better, because if it's running inside of this black hole of the world computer, then it's transparent. It's not owned by anyone necessarily. You can fork it, you can modify it. People can open pull requests against public infrastructure and improve it. It becomes a vastly different paradigm that we would work in. So I think I think this level of scale opens up a whole realm of possibilities, things that we don't even think about. And we will just have to wait and see what people actually build. Thanks for watching. I hope that made sense. I'm not too sure what the next videos will be on. I might break out some of what I've done here and make a standalone 4844 video, a standalone full DankSharding video. I'm not sure yet. I also have videos on Ethereum, an Ethereum overview video, free will, Bitcoin security, etc. So watch out for those, and thanks for watching. See you next time.